Good afternoon. My name is Dale Brocious. I'm the Executive Vice President and Chief Commercialization Officer for IACMI, and welcome to the February edition of Innovation Insights. This episode is being recorded and will be available on our website within a few days. So we just run through a couple of slides here, just a reminder about IACMI and the membership value that we have. Organized around the themes of convene, connect, catalyze, bringing folks together, making those intersections happen, and then letting them go off and do great things together, either by themselves or with, co-funding from various sources, support from experts and facilities that we have. So if you're not an IACMI member, we certainly encourage you to become one. Go to the IACMI website, go under the tab members, and you can fill out a request form, and we'll get back to you with that. So you'll see us not only here virtually, but we'll also be in person at a couple of upcoming events. We'll be at JEC in 2 weeks. It's amazing that March is almost upon us, and we are in Hall 6 in the U.S. Pavilion. So stop by and say hello there if you're going to JEC. And then we will also be at Sampe in Long Beach at the end of May, just before Memorial Day. And then upcoming, we'll promote this much more heavily coming up, but our summer members meeting will be in Indianapolis this year in August. We've got some great activities planned around that, including great receptions and other networking events, as well as a great lineup of speakers, interactive panels, and other features. So just as a reminder, this episode's being recorded, and all episodes are available on the IACMI website. We've had 27 episodes since May of 2021, back starting in the height of the pandemic, or, toward that second half of it. And that's featured over 75 members and partners. So all of those are available for viewing pleasure. They're also on our YouTube channel. Today, we have three entities represented here. And I'll be introducing them shortly. Again, another great lineup around natural fibers, recycled fibers, and some great NDT work going on at one of our university partners. So what I'll say is, before I introduce our first speakers, there is both a Q&A panel and a chat panel. And we'd encourage you to put your questions into those. And as they wrap up their presentations, we have a couple of minutes for Q&A. We'll be able to get to those. So make sure you get those questions in there. So without further ado, I'm going to introduce our first speakers so that they have all the time they need to make their presentation. It's Kyle Huttenlocker, CEO, and Bryan Wilson, President of Environmental Living Industries, based out of Texas. So gentlemen, I'm going to stop sharing and turn it over to you.
Thank you, Dale.
You should be able to start sharing now.
Okay, thanks a lot, Dale. And you can hear me okay?
Yes.
Awesome, thank you. Well, so welcome everybody. Thank you very much for joining us today. We are very excited for this opportunity to introduce you to Environmental Living Industries and more broadly industrial hemp. We understand there's not a lot of knowledge out there about industrial hemp and natural fiber, so we look forward to this opportunity. And really, as a re-emerging resource with huge potential to shake up entire industries, we really hope to provide some essential information about industrial hemp fiber, as well as to offer a counter to some common misunderstandings that some people might have of the plant where hemp is derived. And along the way, we'll use this opportunity to describe to you who we are as Environmental Living Industries, our current capabilities, our future goals, and how we believe that we stand out from other industrial hemp fiber processors, both domestically and abroad. As Dale mentioned, my name is Kyle Huttenlocker, and I'm co-founder and CEO of Eli. Along with me today is our co-founder and president, Bryan Wilson. My background's in government contracting and program management. Following my service in the U.S. Army, I returned to grad school to earn an MBA from Cornell. And I left a 16-year career where I was in Washington, D.C. in 2020 for Austin, Texas, to pursue my dream of building a company. And around the same time, my dear friend and former colleague Bryan here informed me about Eli and what he was working on. And so I did a lot of research into the potential of industrial hemp fibers. And I was pretty quickly sold on Eli and hemp. And I was honored to become part of the team who's going to be responsible for returning the industrial hemp industry to the U.S. market. I'll turn it over to Bryan for a quick introduction from him as well.
Thanks, buddy. Hey, everybody. My name is Bryan Wilson, president and co-founder of Eli. Along with Kyle, I have a background starting as a special operations infantry veteran and a contractor, as well as a paramedic and a firefighter. This was originally a project that was born out of a need for sustainable and natural building materials that actually started about 8 years ago with a long bout of illness with my wife, Candace, who was immunocompromised from a mold-related infection that she contracted in our previous home that actually went undiagnosed by doctors for several years. That actually ultimately culminated in the stillborn birth of my first child, Eli, which is actually where we get our company's namesake from and our mission focus from. And what initially started as a project to develop healthy natural building materials actually quickly changed into a mission to bring natural fibers as a whole into the larger market for a healthier, sustainable impact on a lot more than just building materials. And with that, I'll go ahead and pass it back to Kyle. He's going to go to get started on the agenda and share some of the history that brought us here.
Yeah, thanks, Bryan. The agenda today, we're going to cover just a brief history of industrial hemp, going back to the first use of industrial hemp fiber, all the way up to the 2020 Farm Bill, and even some projections for the U.S. hemp industry. And then we'll talk about environmental living industries, our missions, our goals, and our unique value proposition. We'll cover the hemp fiber processing revolution and talk about some of the state-of-the-art technology that we're going to be leveraging to create some of the highest quality fibers that you can find. We'll talk about where we chose to put our flagship facility is in Dumas, Texas, the advantages of doing business in Texas and more specifically in Dumas, and how we leverage our relationships with our farmers to provide the highest quality fibers that we can. And then finally, we'll talk a little bit about our products and our interim distribution operation. Essentially, it's a distribution operation where allowing us to provide high quality fibers today at a domestically produced price before we're even operational. So yeah, a brief history of hemp. Industrial hemp's a variety of the cannabis sativa plant species, and it has a storied history dating back, thousands of years, quite honestly. It was initially cultivated in ancient China for its fibers to be used in textiles and ropes, quickly spread across the globe for various uses, including paper, food, and medicinal purposes. And then by the 20th century, regulatory restrictions in many countries significantly curtailed its production due to its association with the psychoactive varieties of cannabis that we all know as marijuana. In recent years, a resurgence of interest in sustainable and eco-friendly materials has actually led to a revival of industrial hemp cultivation, and that was fueled by changes in technology, advances in technology, and changes in legislation. Specifically, the 2018 Farm Bill marked a pivotal shift in the industrial hemp fiber industry in the United States by legalizing hemp cultivation and removing the plant from the federal list of controlled substances. This legislation distinguished industrial hemp from marijuana by setting a THC content threshold of 0.3% or less. That really opened the door for widespread cultivation, research, and investment in hemp and its derivatives, which is catalyzing the growth of the hemp fiber industry in the U.S. by enabling farmers, entrepreneurs, and companies such as Eli to begin to explore the material's diverse applications, specifically in composites, textiles, construction materials, and much more. I'll turn it over to Bryan real quick to talk about who we are and some of our missions.
All right. Who we are. Eli is an expeditionary, veteran-owned and operated startup headquartered in Austin, Texas. And Eli stands at the frontier of the modern industrial hemp revolution, transforming raw hemp into an ideal sustainable fiber ready for use in thousands of different industries, including composites, nonwovens, textiles, absorbents, construction materials, and scads of other applications. We are very excited that our fibers are also suitable for adoption in some of the more advanced material applications, such as bioplastics, aerospace technologies, and energy storage. Our inception was timely, coinciding with hemp's reclassification as an agricultural crop in the United States with the passing of the 2018 Farm Bill. Our unique position in the U.S. is not just about introducing an entirely new natural fiber resource, but also setting a benchmark for sustainability and quality through hemp fiber production. As we prepare to begin our domestic processing operations in 2025, our vision is clear. To establish Eli as a premier hemp fiber processing company in the U.S. and driving demand for American-made hemp products and supporting our nation's environmental initiatives.
Awesome. Thanks, Brian. Yeah, so what that means is we believe the U.S. market's ready for widespread adoption of industrial hemp fibers into extensive variety of different industries. Industrial hemp fibers' unique and vast capabilities means that it's going to be an environmental and economical alternative to many of the materials used in manufacturing thousands of different products today. However, so far, demand has far outpaced supply, and a reliable supply chain of high-quality fibers has yet to be delivered by any U.S. hemp fiber processor, despite their best efforts. Companies across the country are pretty excited to incorporate hemp fiber alternatives into their broad mix of offerings, but there's still a lot of research and development that needs to be done. And without a real clear path towards a sustainable and reliable supply chain that really just considers the scale and quality standards that are required by the American manufacturing industry, most of these efforts are stalled. So it's this environment where Eli has distinguished itself to have the most impact by virtue of our scale and quality. We look to provide U.S. manufacturers with a reliable supply capable of meeting their industrial scale needs of the highest quality industrial hemp fibers. And we understand that widespread adoption of the industrial hemp fiber industry in the U.S. market requires a processor to fill this void. So that's where we set out to build a business model that's optimized to this value proposition, which we'll cover.
So the first step that we took towards the goal was to identify a processing line that maximizes our fiber quality and can be scaled to meet our future customers' industrial scale needs. So we found such a processing line from a European company called Cretus. European manufacturers have the best hemp fiber processing technology since the regulations have allowed for the cultivation of hemp in the EU since the 90s. Cretus, which is part of the Vaultec Group, is renowned for its expertise in the development of manufacturing of industrial hemp processing lines. The state-of-the-art 4-ton-per-hour system incorporates cutting-edge decortication technology, ensuring that the fibers retain their strength and quality essential for the diverse applications that they're going to be used for. One of the key technologies employed by Cretus for decortication hemp is the use of roller technology and the scutching machines instead of actual hammer mills. This technology is designed to efficiently separate hemp fibers from the woody core, aka the hurd, without significantly damaging the fibers, which is a common issue with hammer mills. Coupled with the advanced air separation system, the line meticulously removes dust and small particles, resulting in clean, high-quality hemp fibers ready to meet the most stringent specifications. Cretus's innovative processing line stands as a testament to our commitment to sustainability and efficiency, which makes them a valuable partner for Eli as we look to expand our domestic industrial hemp market, providing the tools necessary for high-quality hemp fiber production, suitable for a variety of end uses, from composites, construction materials, to textiles and beyond. The system is designed with the future in mind. It is immediately scalable to a 7-ton-per-hour system to adapt to our growing demands and evolving market needs. This flexibility ensures that Eli remains at the forefront of the industrial hemp revolution, capable of scaling operations quickly, efficiently, and sustainably.
Awesome. Yeah, so after determining what line we wanted, we sought out next to find a region where we could maximize 3 critical advantages that we identified. We wanted to maximize agricultural capability, local economic support, and geographically based logistical capacities. So looking at the United States, we really understood Texas to be an attractive state for the industrial hemp fiber industry due to the proactive stance of the Texas Department of Agriculture under the leadership of Commissioner Sid Miller. Also, Texas's business-friendly regulatory and tax environment, combined with its vast agricultural capabilities, also with the geographical location within the continental United States, including the seaport access, really made Texas the ideal state to locate our first processing line. And then a further evaluation of the agricultural and geographic potentials of the state drew us to take a close look at the Texas Panhandle specifically. After speaking with a number of Chamber of Commerce, City Council, Economic Development Corporations in the North Plain region of Texas, we landed on Dumas, Texas, and Moore County as the optimal home for Eli's flagship processing facility. Centrally located halfway between Dallas and Denver in the Panhandle, Dumas is a distribution hub for transporting goods by rail, road, and air. Dumas is ideally located along highways 87 and 287 of the Ports to Plains Trade Corridor, which is a multimodal transportation corridor that includes multi-lane divided highways and rail lines. And then just south of Dumas, near Dallas, sits the east-west conduit of Interstate 40. Dumas is also located critically along the Burlington Northern Santa Fe Railroad lines and is site of the Texas Northwest Logistics Center, which is the largest rail car park in North America. If you haven't seen it, it's quite impressive. If you ever find yourself in that area, I encourage you to go take a look. The future home of Eli's processing facility is on an 18-acre lot in the 265-acre Dumas Business Park, which is just north of the town, which we were able to secure through support of the Dumas Economic Development Corporation, who's been a huge proponent of us and quite supportive. In terms of agricultural capabilities, today, Moore County has over 250 farms that growing on 480,000 acres with an average farm size of just about 2,000 acres. 46% of these farms utilize no or reduced till farming practices, which create less water usage while retaining the soil's nutrients and creating a cover for new seeds. Water is the prevailing concern regarding Dumas's farmers. The city's water conservation district has been hailed as the most progressive and innovative district in the nation for its approach to water conservation. This program is actually widely supported by local farmers, and most adhere to their own self-monitoring. However, with these practices in place, Dumas farmers are continuously seeking alternative methods, alternative crops, and farming innovations to help continue operations while utilizing less water. It's a big concern for them. So what's great is industrial hemp fiber crop production is widely attractive to these farmers in the region due to the crop's reduced water needs, with many cases showing water consumption levels required to grow hemp near half of those required to grow cotton or corn. And currently the chief crops grown inside of the Dumas or Moore County is corn, sorghum, and milo, wheat, and cotton. We've actually secured contracts for our hemp production needs with Moore County farmers who collectively farm over 100,000 acres. These are large operations. The lots operated by these farmers for the cultivation of our raw material are all located within a 20-mile radius of the Dumas Business Park and the future site of the Eli facility. This is going to allow us to benefit from reduced logistics costs and significantly increases our quality control capabilities. Moreover, because our farmers grow hemp directly for Eli, we're actually able to grow for each customer's unique needs. So from the moment the seed is put in the ground, we can control the fiber quality and specifications by leveraging things like seed genetics, acreage, density, stock height, redding practices, and many other farming practices. So we've got a lot of levers to pull for quality control measures. Finally, this unique business model is when you combine it with hemp's natural carbon sequestration capabilities, means that Eli expects to deliver a carbon negative product to any manufacturer facility within the continental United States. And to prove this, immediately upon reaching our full operating capacity, we're going to conduct a life cycle analysis on our model and our products to provide the customers with third-party verification of our operations carbon footprint.
So what do we offer? Okay, so we offer through a zero waste, all mechanical processing line, a range of natural fibers pulled from every part of the plant, leaving nothing unmonetized. Excuse me. Our long and short fibers are harvested prior to full maturity of the plant. Doing so elegantly avoids any threats of any THC limit violations, while simultaneously also providing more supple fiber that hasn't had its integrity degraded from the formation of the crop's top structures, pulling from the think veal instead of beef, actually. Our process allows us to finely tune our fibers, especially for the fiber market, by avoiding the lure of attempting to serve two masters from dual cropping with fiber and grains. So with no chemical interactions, close proximity to the farmer, all within 20 miles, and some of the cheapest energy prices in the world that are heavily fed by natural gas and wind generation, we will serve as a remarkably high standard in materials for LCAs and reductions and even reversals in some cases in climate impacts. Our herd material, or shiv, is the inner woody core of the plant. This is immediately usable as a natural sustainable material for building materials, absorbents, pulping, as well as hemicellulose and lignin extraction due to its high natural composition of the substances. And last but not least, our dust material is collected via negative pressure and deposited at a collection point at the end, ensuring that nothing is discarded. And the hemp dust itself makes a great mesh material for further applications of absorbents and binders and biofuels.
Yeah, great. So we're happy to announce that anybody interested, doesn't need to wait until we complete the construction of our Dumas facility to procure some high quality hemp fibers from Eli. What we're doing is, in order to generate near-term market demand, we've developed what we call an interim distribution operation, which allows us to import the exact same quality fibers that we plan on producing domestically. These fibers are imported capable of meeting the composite industry's strict specifications per each customer's order. And then we want to provide them to these U.S. manufacturers at the same market price that we plan on providing once we're operational with our own processing line. You might wonder how we're able to do that. And to be honest, we're only able to conduct this distribution operation on account of our near-term Series A offtake requirements, really by leveraging our relationships with European suppliers that we've developed and then structuring our near-term finances around market generation instead of near-term profits. We're able to be the first distributor to offer U.S. prices for hemp fiber of European quality. So we hope that that's attractive to some folks. We do have a full technical data sheet that can cover a variety of different technical information on our fiber, but I wanted to highlight a couple, particularly the pre-cut fiber staple length. You can see how the distribution works out on the length of the fibers. But what can be done with a little bit of value add is the fibers can be created or put into a sliver and then cut, at somewhere around, say, 20 millimeters. And then according to this graph, everything to the right of that 20 millimeter mark would fall down right in line with that 20 millimeter, providing you a really tight length distribution, which we hope to do. We are searching partners now for the capabilities to do any kind of combing and creating slivers for us. So if there's anybody out there that has these capabilities, we certainly would love to talk to you. We encourage you to reach out. And then we also want to highlight, the breaking strength of our single fibers. We understand that we need to have some technical discussions with folks in the composites industry, and what we've done to that end is we've gone out and hired a couple of technical consultants. So for any highly technical data sheet questions that we might have, we're more than happy to share the technical data sheet with you and then pair you with one of our technical experts at any time that would be happy to dig in a little deeper on these technical data points as we have further discussion. So that's it for us. I really appreciate the time that everybody's taken to learn a little bit about Eli, and I hope we were able to educate you a little bit about industrial hemp fibers. Here's some contact information for us, and I know Dale will share that with everybody as well. And then I would just open it up to questions and kick it back over to you, Dale.
Yeah, we're kind of running tight on time, Kyle. But there is a question in the chat, and I've got others but I think suffice to say, you are looking for partners that can do downstream processing of these fibers, whether that's twisting them, combing them, putting them into mats, putting them into other forms. Don Woods asked, can you provide, for example, 1/8-inch fibers? Sounds to me like most of what you're going to make is a bit longer. But
Mm-hmm.
for example, a company like Mini Fibers might be able to transform your fibers into, the 1/8-inch that somebody's looking for.
Yeah. So as the fibers come out of our facility, they're not all lined out like they would be in a sliver, and you have a wider variety of different distribution lengths. We've actually been having a lot of very progressive conversations with Mini Fibers. What's missing between us and Mini Fibers is somebody that can actually take that fiber, comb it out into a sliver so that Mini Fibers can cut it evenly. And we're searching for opportunities in that regard at this time. But we don't have the intent to integrate into any particular industry at this stage. So we are certainly looking for partners that can help us do value add, understanding that much of the value chains need to be developed between us and manufacturer and end user. So we're very interested in having conversations with any company that is looking to do those value adds. What we can deliver to you as a supplier, and in many cases, a customer. So please reach out.
Good. Well, I'll remind everybody, if you've got some additional questions, put them in the Q&A or put them in the chat, and Kyle and Brian and Chris will go to answer those live time. There is a comment in there about some life cycle analysis you might want to take a look at.
Okay, yeah, we'll take a look.
Yeah, and I do know online we have Michaelman, who's a supplier of sizing that probably a good partner to be working with as well. So
awesome. Well,
all right, thanks. Okay,
thank you.
Good. Let's move on to our second speaker. Is Jeff Hall. He's the Director of Client Relations for Carbon Fiber Recycling LLC. I'll just throw her into slideshow mode, Jeff, and we'll be ready to go.
You guys can see my screen okay, Dale?
I do.
Okay, got it. All right, guys. Well, hey, thanks for inviting me, Dale, Kim, and IACMI team. So I've got about a 30-minute presentation. I'm going to shoehorn into about 10 minutes here. So I'm going to go quick on some of this stuff. Bear with me just a second. Let me get back to the beginning. But I'll get through it pretty quickly. We got opportunities for questions. And of course, my contact information is part of this. So you guys can reach out to me at any time. So basically all we're going to do is give you guys an update of kind of who we are, Carbon Fiber Recycling. Some of you are probably familiar with as a little bit of a company overview and update about our product. Brief agenda. Don't really need to get into that. You guys will see soon enough. So sustainability challenges. Going into a presentation, when we meet with folks, we'd like to kind of understand their business, right? And what are some of the challenges they're focusing on and hit with. And so for this particular presentation, we wanted to take a look at just sustainability challenges. And I think these three really encompass just about every business out there. So upholding sustainability while maintaining competitiveness, obviously that's tough, right? When your competitors maybe don't put the effort into sustainability that you do, there's some cost impact and just resources that get tied up in different things that can impact your business as a whole. The other issue is you grow your company, your end of life materials, production scrap, things like that tend to increase alongside you. So what do you do with those materials? And oftentimes it's kind of overlooked as part of the growth strategy. And then increased regulatory pressures, right? So we all, probably have certain things that we would, love to do from a sustainability perspective. And then there's things we have to do from a sustainability perspective, right? And those regulatory pressures seem to be increasing. So this is kind of where we fit in. This is what our company is set up and designed to do. So a little bit about our company. We were founded in 2018 by Doug Griffin. We're located in Tazewell, Tennessee, which is kind of northeast corner of Tennessee. Our production capacity is about 3.5 million pounds of recycled carbon fiber a year. I'll get in a little bit into that process here in a second. But the best way to think about it is, and I hate to use this analogy, but I'll do it anyways. Think of a meat grinder, right? You cram materials in one end, and out from the other end comes recycled carbon fiber. So as long as you're putting material into that one side of it, it will continuously come out the other end. So a little bit different than the way most folks are doing this. Most folks are recycling carbon fiber globally today. We provide a dedicated closed loop technology. What that means is you can send us a product, we will recycle it, we can send it back to you. When it gets end of life, you can send it back to us again. We can send it back to you with some degradation, which simply means that degradation is probably not the best word. The material will continue to be kind of downsized each time that it is recycled. So what we run into is the components that you're going to use the recycled carbon fiber in can evolve alongside with the recycling of that carbon fiber. We can also do very large quantities, which recycled carbon fiber has been kind of overlooked in the past for certain types of applications because there was some supply chain anxiety related with the product availability. But at 3.5 million pounds per year at this one facility, I think we've got production volume substantial enough that we can overcome those anxieties. And at the end of the day, what we produce, when this material comes from our pyrolytic reactor, what we've produced is a very clean, pure carbon fiber that is recycled. So let me just jump on to the next slide here. So distinguishing characteristics, essentially, these are the things that our customers, people we've done business with, say distinguish us from some of the other folks, other type of products and things like this that they've worked with in the past. So at the end of the day, you know, we use a scanning electron microscope to verify the quality of the material. We independently verify the material as well. It's clean, it's consistent, it's quality controlled. We have the capacity, like I said, to overcome the supply chain anxiety. It's very low emissions. So somebody mentioned something about life cycle index earlier. When you take a look at the life cycle index of virgin carbon fiber, and then you take a look at this product that we're producing, our product has less or greater than 90% less of the life cycle index than virgin carbon fiber, which is massive. It's very substantial. And then our process that we manufacture at this continuous closed loop pyrolytic process actually has an opportunity to become negative, carbon negative, by capturing the syngases and utilizing the hydrocarbons to actually fire the reactor. So the more material we put in it, once it's up and running and started, the more it drives you toward carbon negative. So we're pretty proud of what we've been able to accomplish there. So acquisition. So essentially the way our company operates is we have recycling agreements that we enter into with several of our clients. So they give us pre-preg, you know, other types of carbon fiber, epoxy, you know, type material that comes in. We get the production off-fall, as well as end-of-life material that comes straight from the field. So we take that material and we grind it up in shears, shredders, granulators. We separate the metals. Sometimes there'll be materials that think of like a cardboard core, some things like that that we'll remove the product from. And then it goes into the process. So essentially it's a conveyor system, like I said, that separates the materials, and then goes through the pyrolytic process. And then when it comes through the other end, we end up with 6 millimeter, think of like a cotton, if you will, only carbon fiber. So we take this material and we have a baling process that we've designed that allows us to really super compact it into very, very tight bales, 250 pounds plus. And we do this just for ease of shipping, right? Carbon fiber doesn't weigh very much. So unless you can get it packaged in that type of through that type of process, it can be quite expensive to have to move it around. So we're pretty proud of the way we're able to kind of bundle it. Any of you guys have ever bought any like blow-in insulation or anything like that, and you've seen it super compacted, wrapped in plastic, think of that as being what our bales currently look like. You know, just talk a little bit more about our product. So essentially, like I said, I mentioned earlier that this product is very, very clean, 95% or greater, you know, depending on how you look at it compared to other products. Custom link processing, essentially, you know, the way this material comes from the pyrolytic process now, you know, we've captured it at we've set it up at 6 millimeters. We've done this because we're in the process of pelletizing this material into different types of compounds to be used in molding applications. So 6 millimeter kind of seemed to be the sweet spot for us. Reality of it is we can get that all the way up to 25 millimeter if we had a use for a longer recycled fiber. It's very consistent. You know, no matter what you put in one end, all that comes from the other is the carbon fiber. You know, we do some pre-sorting to remove cardboard, you know, things that could have minerals that would impact that process, as well as glass. So all that material was called out before it actually enters into the pyrolytic process. So it's a very versatile material stream that we can bring in. Like I said, we can handle as well as end-of-life products. We can do, you know, material off-fall from manufacturing processes, pre-preg materials that are out of spec. If it's got, typically we like to see around 30% carbon fiber content or more, we can find a way to recycle that material. So here's a shot of a study that was done at the University of Tennessee, and I've got a lot more information on this if you guys want to get your hands on copies of it. But you can see that recycled carbon fiber in some aspects performs better than other fibers in ultra high performance concrete. It's just one of the markets that we're looking at. So we were compared with steel, neat concrete, which has no fiber additives whatsoever, and virgin carbon fiber, one sized, one unsized. And they did a comparative analysis. There was several ASTM tests involved in this process. And here are just some of the results. And like I said, if anybody's interested, we've got the complete study by the University of Tennessee. There's nothing proprietary about it. You guys can get your hands on it and take a look at it. But it's a pretty telling story when you start to see how this particular fiber can stack up against virgin carbon fiber. And the reality of it is, it's a fraction of the cost. It's sustainable from a sustainability perspective. It's the right thing to do is to utilize this material. So at the end of the day, sustainability is a big piece of what where we see ourselves fitting as a business partner with different organizations. So one thing we do from a sustainability perspective is we help them lower their LCI. So by designing in and utilizing recycled carbon fiber, they can reduce their overall LCI for the products that they manufacture. And like I stated earlier, we're a continuous flow. There's other people out there that do things with pyrolytic processes and pyrolysis. I hope I'm saying that correctly, but where there's other types of methods to extract carbon fiber and recycle it. But the problem is you get into that supply chain anxiety. They're typically small batch related processes that are good for novel type studies and things like that. But to really be successful in utilizing this product into manufacturing, you got to be able to do it at scale. And that's what our company is invested in. Circularity is a big part of what we're doing. And by circularity, I think you guys all know you have recycling, sustainability, circularity, and there's some philosophy around those three things and what they mean. But from circularity in this regard, gets into this closed loop perspective that I was telling you earlier, where we can bring material in, we can recycle it, it can go back out, it can be reutilized for other applications, and oftentimes within the same industry and even the same company, which is a pretty positive. It has a pretty positive impact on those companies' sustainability initiatives. Give me just a second, guys. Sorry, my video was in the way of this last bullet, but contaminant tolerance. We have a very large ability to tolerate contaminants because the pyrolytic process essentially eliminates everything except for the carbon fiber. And through this process, like I said, we capture hydrocarbons. We use those to fire the reactor. So the more we put in, the more efficient we become. The more we manufacture, the more efficient we become. And it drives this, like I said, this process down into a carbon negative situation. So at the end of the day, working together, right? This is the business fit of it. Like, what does carbon fiber recycling bring to your company? It's a couple of different things. If you utilize carbon fiber for your process, you end up with some production capacity relief, right? So we can take pressure off of the existing carbon fiber industry. If people are buying compounded, and short length carbon fibers all the time for different type of thermal projects. You've got utilization in other types of materials, electromagnetic shielding, and so on. And they're buying virgin carbon fiber. When the reality of it is there's an overwhelming abundance of carbon fiber materials out there that can be recycled, used for these types of projects without any degradation to the product whatsoever, and in some cases a better performance. So we can also help companies realize their sustainability objectives, right? And then at the end of the day, the reason why we're all here is profitability. You can't gloss over that. So, recycled carbon fiber is substantially less than buying virgin carbon fiber. The material's already been utilized once. We bring it in, we recycle it, we get it, utilized for a new process or product. And you have increased profitability. Like I said, without profitability, I don't think there's too many of us that would be here today. So that's a pretty important aspect that we bring to the table. So I know I went through it very quickly, but Dale, hopefully I got us a little bit of time back. And And that's it. So you guys can see here, I'm the director of client relations. That's a fancy way of saying that I handle both the outgoing sales side of things, but also manage the incoming side of things as well. So if you guys have any questions related to either one of those things, you got my contact information here, and feel free to reach out to me.
Thanks, Jeff. We have time for a question that did come in. Was that pyrolysis presumably removes the sizing and coupling agent from the fiber surface? Do you add that back in? So do you size the fibers at the end?
Right now, the answer to that is no. We've not had an application that requires that. However, it is something we understand certain clients may have a need for, and there could even be certain compounding applications where some level, some type of sizing may be required.
Okay, so is that something you're looking to offer in the future?
Yeah, definitely. If a particular client had an application for the recycled carbon fiber, viewed it and that sort of thing, but it only worked with a particular type of sizing. We've got colleagues and folks that we work with that are sizing experts that would, work with us to develop the appropriate sizing for that product. The problem with it is there's not a one size fits all, right? So we would have to look at it from a case by case basis,
Like I say, our friends from Michaelman who are online make sizings for thermosets and their various thermoplastics as well. So I think that Steve will reach out to you.
Perfect.
All right.
All right. Thanks, everybody.
All right. Hold on. One more question. Question that comes in is, how is your supply and do you produce different grades? So,
yeah, if I understand the question correctly, when the material comes in, we get a mixed, what we would consider to be mixed grade. We don't always have the ability to know, what comes in. We do have a sample submittal form that customers will provide us. They'll give us as much information as they can about the carbon fiber. So we do manufacture what we would call like mixed modulus. However, if there was a particular use that had a requirement for a specific modulus of carbon fiber, we can manage that. We would just simply pre-sort, identify that particular modulus of fiber, and then that's what we would run through the pyrolytic reactor, for that customer. So can be managed, but I would say right now would be what we would consider be mixed modulus.
Thanks, Jeff.
Yep, you bet.
Appreciate it. You can stop sharing, and then we'll bring on our third and final speaker of the day. And our third presenter is Dr. David Jack. He's a professor at Baylor University, in the great state of Texas. So we've got two presenters from Texas today. So, David, take it away.
Thank you very much. I want to thank you. I want to thank the entire IACMI team for the opportunity to speak to you today. I'm a faculty in mechanical engineering. I'm also the director of the new material science and engineering program at Baylor University. And I'm representing a handful of faculty, part of what's called the Scientific Innovations and Complex Engineering Materials Group. And we do a variety of testing and modeling and characterization across the spectrum for complex materials. With everybody, let me go ahead and give a quick kind of an introduction. The university, yes, another Texas mark for today. We are chartered by the Republic of Texas. We are the oldest university in the state of Texas. We were founded for the church and for the state, and we continue that way to this day. We have enrollment of a little over 20,000 students, 5,000 of which are graduate students. That's a program that's been growing a lot. Engineering is relatively new at Baylor. And I guess kind of the highlight is in 2006 is when we started offering a bachelor's and a master's in mechanical engineering and then also in electrical engineering. I showed up in 2009 as the first mechanics and first materials hire in the group. In 2014, I was able to create the PhD program in mechanical, and 2024, the PhD in materials science and engineering. Today, we have about 16,000 square feet of space that I manage in what we call the Baylor Research and Innovation Collaborative. We're here on the second floor and the third floor of this building. And I have another about 9,000 square feet of space that's ready for me to expand into over the next 2 years. We have 6 faculty, 35 graduate students, just under 10 full-time technical staff, and a wide variety of undergraduate research assistants, all of us work in the area of complex materials. We've been very blessed to receive funding from a wide variety of sources over the last decade, and looking really to expand that group that we work with and partner with. So what do? We do a lot of work where we start at the microstructural level, whether you're talking about individual voids, individual fibers, where they're placed, where they're aligned, the polymer itself, and how this builds up into the full component and structure. From there, we look at the lamina properties. Now, maybe the word lamina is not quite the right word on this one. Maybe a more appropriate word is maybe more like at the, not the micro scale, but the millimeter-ish length scale. We do chopped fiber, we do discontinuous fibers, and we do layups as well. And so looking at something at a larger length scale than individual fibers, but not quite to full component. We then also do a lot of work on the design side on the component and full-scale structural tests of components themselves. Now, a lot of those things, that's nice, that's very academic in nature. But really, it's the applications that we focus on that then blends us from the university to the industrial side. We look a lot of high-rate manufacturing, whether it's in the automotive world or whether it's in the aerospace world. On the automotive side, we tend to do a lot of stuff in chopped discontinuous fibers for a lot of thermoplastics. On the aerospace world, we do a lot of stuff with thermal sets and layups for the aerospace world. Whether it's ranging from maybe a honeycomb with a compromised core from a manufacturing process to some kind of damage that was occurred during the drilling process as you add a fastener, to bond line characterization, to essentially full life cycle assessment of the as manufactured part. We do some stuff in the area of the wind field where we look at both lightning strike propagation and inspection, how that behaves, and all the way to wrinkle identification and quantification. Especially when you start getting to your thicker structures here at the base or at the root, you have a tendency to have internal wrinkles. And imagine a rope that's bent doesn't carry as much load as a rope that's straight. And so that's what we're looking at, is looking at the internal features within larger structures. We also do some stuff with in-service life estimation, whether you have a one-off part or whether you have a component in front of you that have some level of damage, essentially estimating as that damage grows off in the future and when you need to make essentially a critical decision on either repair or replace on this one. And we also do some stuff with impact damage that I'll get into in a few minutes. Let me talk about a couple different applications. And really what I want to get is kind of a story from each of these. We go all the way from the deep theoretical side all the way to the final as manufactured performance. So let me look at the drill hole process. Again, this is just one of our many applications, but I'm drilling a hole into a composite structure. During the drilling process, I induce delaminations. I then put a fastener to bolt this to something else. The problem is these delaminations are not necessarily consistent part to part or even hole to hole within the same part. And so what we're wanting to know is the actual as manufactured performance. So we have an ultrasonic scanning system that is out of the tank, so we don't need to do this inside of an immersion tank. This can be done inside of a manufacturing environment, full robotic control for this, a fairly rapid inspection that we can do from this one. And actually the part that you see here, this is actually a component we got from Letterkenny Army Depot. And for the moment we pulled it out of the box and said, all right, let's go, and set up the system and everything. It was less than 30 minutes to actually having data analyzed, but that was having an unknown part. If we were to do this in a manufacturing environment, typical scans on the order of seconds to not even a minute, depending on the size of what we're looking at. So we take that data and we have the full acoustic waveform. Now, unfortunately, the colors on this are flipped. Red is actually good. In this case, blue is bad. We capture the full acoustic waveform, and the red regions are undamaged, whereas the blue region is damaged, and the white region or the hole is, well, the hole. This is a drill hole, but this essentially changes as a function of depth. We then automatically extract from there a three-dimensional surface profile of the damage. Now, that three-dimensional surface profile is unique to the part itself, unique to the hole itself. From there, we take a layer-by-layer extraction of this delamination. This is typically where inspection stops. You then go into some kind of book, or you go back to some engineer and say, is this okay? Is this acceptable? We don't stop here. We take it to the next stage. We actually take it to the layer where we say, okay, let's look at each individual layer. And we now feed this into a fine element model. This now takes the three-dimensional geometry from the inspection into the computational domain. From the computational domain, we're able to obtain things like the strain field. And that's what you see here on these bottom pictures. These are 6 different loading scenarios, and you see the various levels of strain increase. Same color bar. The top are the digital image correlation pictures. Our model, from the actual physical three-dimensional geometry from inspection fed into a fine element domain, yields the identical strain field behavior as what we're seeing in the lab. And this is unique to each individual part. Then the damage zone, we essentially are able to, and that's what the colors here represent, the nature of the damage, not just delaminations, but fiber breakage, matrix breakage, those are each of the different colors, aligned with the actual physical test that we perform. From there, then an engineer could look at a stress concentration factor, reduced life, load, and expectancy. And now you can use this in a design process or essentially a qualification process. And so this is all done from the inspection data of the physical part. Second application, wildly different application. My hat's off to the Oak Ridge team and Oak Ridge folks. This is a derivative of the BAM process, large area additive manufacturing. This is actually with my colleague, Dr. Douglas Smith, his student. He and I have been working on this for about 15 years or so. And then he's now partnered with Chad Duty, who University of Tennessee, Knoxville, and also is very familiar to IACMI. This is essentially a pellet-based system that's here. It extrudes out on the platen, and from there you get a 3D printed large volume part. But within that, you have various different types of defects. You have the defect from the voids between the individual layers, the interbead, and the intrabead void. Well, we take that information and we take the geometry itself as printed and look at a high-resolution CT image of the parts. Now, what you see here, and it's really hard to see on the video here, so let me go ahead and zoom in a little bit. What you see here are individual voids showing up within the part. Now, these voids are, well, they're not structural in nature. Not only that, we have the individual fibers inside of here. Now, this also varies spatially, whether you're looking at the top of the part, the middle regions of the part, or the bottom of the part. There's a lot of spatial variation. And then we take those spatial variations and feed them into a fine element framework. And so essentially you have spatial variations in fiber orientation, in void concentration, in the shape of the void behavior, and you can feed this into some type of model. So one of the models that I'm just going to show here, this is just a deposition model. Essentially, you're looking at the thermal profile as you lay down each individual layer. And this is a different thermal profile than what the actual neat behavior would look like. Neat being no voids, perfect fiber alignment. This is actually the real thermal profile of the physical part itself. Now you can better understand the behavior within the composite and also from the manufacturing behavior because you have this high resolution inspection data. Third application, and this is where a lot of universities start to, I'll say, stumble. Universities are great at TRL1 through TRL3. We're really great at getting that journal paper out and deploying it and patting ourselves on the back and say, good job, everybody. We actually take it to TRL6. TRL6 is this is now ready to go. It's been proven in the appropriate environments, and it has essentially appropriate federal or oversight standards. In our case, for the studies we're going to look at are these FAA 8100-9s. These are statements of compliance with airworthiness standards. Each of these tests will be performed or overseen by an FAA DER, a designated engineering representative, and essentially the entire test plan. Some of our test plans involve as small as 50 parts. Some of them involve as many as 1,400 coupons that we're looking at for different features that we're trying to qualify. Let me just give you a flavor of what I'm talking about. Barely visible impact damage. This is something that can occur maybe from a bird strike, a hail impact, worker tool impact, maybe foreign object debris coming in from the ground during a landing or something, but something causes a bump in the aircraft. And you look at it and you go, I think I see a scratch, but I'm not sure if that scratch is important or not. Not really sure. Let's inspect it. When you come into the inspection, you will end up getting a three-dimensional damage zone. That actual three-dimensional damage zone, not the surface image, but the subsurface behavior. Now you can make a proper decision. And then we go back to feeding into the fine element framework. We've actually, for this specific one, for barely visible impact damage, we have 3 different FAA 8100-9s for different versions of this BVID, or barely visible impact damage. And the key word here down here is we were able to get this for every single panel. We were successful in identifying and quantifying in every single panel. 100% confidence we achieved it. Everything is validated using X-ray CT. What do? We make the part, we hit the part. We hit the part with a controlled series of energies to get different types of damage. We then inspect the part out of the immersion tank. This is not done inside the water. This is outside of the immersion tank that we do this. We then extract the waveform from the acoustic side. And from there, we get an automated extraction of the damage profile at a layer by layer. This is a 3-dimensional damage profile, not a 2-dimensional, not a surface damage. This is a subsurface. We then validate with X-ray CT. And at the end of the day, we can check the accuracy. And actually, we came into an interesting quandary here where actually our UT, we believe, is actually more accurate than CT, but CT is considered the gold standard. So our ruler that we're calibrating against, we feel we're actually better than the ruler we are calibrating. We have some papers coming out to kind of show that in the near future. So what we have is in this particular study, we had 45 different, they were called a hybrid carbon fiber panel. They had a unique weave and unidirectional layup on it, all the way from undetectable to detectable. We found every single region of damage to within 1 millimeter of the CT damage zone as a function of depth. Now we've done this for 12 different 8100-9s, ranging from in-service damage, barely visible impact damage, to manufacturing induced damage or manufacturing based quantification. For the ply stack orientation to bond line thickness qualification to foreign object detections like gloves and peel ply sitting inside the composite. So we do this across the whole spectrum for each of these. And we have more lined up and ready to go. We're not limited to just those 4, whether you're interested in eddy current inspection for subsurface cracks or what they call marcelling. Essentially, this is in-plane waviness, to wrinkle detection, to honeycomb quantification, to incomplete bond line. We have a series of these ready to go if they were needed to go forward for certification. And we also have the facilities to do the certification. What I mean by the facilities, we are an ISO 17025 accredited test lab. This is rather unique for a university in that we actually can do testing services for industry partners, and we can actually put the ISO stamp on it. So we have a series of tests within our scope. We also have a series of custom tests that we'll perform that are off scope, but is needed for very, very specific applications. What's unique about this from a university perspective is they're able to take essentially testing components or coupons almost the day that you need the testing done. So we've actually done some stuff in less than a 24-hour turnaround time in an emergency pinch basis. We prefer a few more days than that, but we are able to do rapid testing services as needed on demand. Trying to think of some potential partnership areas with IACMI members. Looking at the high rate aerostructures, looking at in-process inspection automation for rapid component qualification. We can actually look at part by part at the speed at which they are manufactured and fabricated. So instead of pulling them off online, instead of generating tons of components and looking at each one of those, and then going in and doing the manufacturing, we can actually look at the part that is made, at which can then go into service from that. We also have extensive experience with the 8100-9 process and are ready to spool it up as needed. Looking at the area of future mobility vehicles technology, I know there's a lot of stuff going on the enclosure and also around the battery side. We're doing a lot of unique stuff in the area of eddy current inspection and looking at multifunctional structures, and so looking at different areas on the battery enclosure and EMI shielding. Final area, would love to talk to some folks about the wind energy side, looking at component level inspection and qualification. Those pose some unique challenges in what you make due to just the length scale. And we're able to scale up rapidly from an inspection perspective to larger surface areas, larger volumes. We're also able to look at embedded wrinkles and understand their impact on final part performance. Looking at, and I'm going to speed up, I see we're almost done. So looking at kind of 3 specific technology applications, we're able to identify defects within additively manufactured components and looking for partners on how to support us and identify automated analysis of feature identification within there. Really need to know more about what are the defects that are of concern to partners out there in the industry. Spoken about this a couple times in the area of wrinkle characterization. We can generate 3-dimensional images of each individual lamina within the composite and take this all the way to a structural analysis, looking for folks to partner with on both an application side of this and also to better understand this multimodal failure behavior that's caused by these unique features. Last area is on multifunctional materials, battery enclosure specifically. We've got some unique technology that we've developed on the area of eddy current inspection that doesn't exist out there in the market. And looking forward to folks to partner with on that one who have either chopped discontinuous semiconducting fibers or conducting fibers inside of some type of matrix or system. With that, I cannot thank you enough for your time, and I look forward to the conversation. Any questions that may be out there?
Thanks, David. I've got a question. On a solid laminate structure, what do you think the maximum depth you could accurately predict location of damage?
Yeah, the how deep we can go is going to be a function of how small of a feature you want to see. We've been looking at some 4-inch thick components from the wind industry and also on a product that's made up in the DFW area for an aerospace partner. And we can go about 4 inches thick on those and identify some of the damage there, but definitely not at the sub-millimeter resolution.
Right. Okay. Yeah. Yeah, I think it's it's pretty consistent with everything else. But there are very few structures that are anywhere close to that thick.
Yeah.
I mean, obviously in a wind, the only place where you get that thick is in the root, and then I guess potentially in very, very large spar. But
Yeah, we've done some stuff with large spars with helicopter blades, and then also the root on the wind turbine.
yep. Okay. Well, great. I appreciate that. And yeah, I definitely will point this presentation toward a few of our working groups that I think could take advantage of some of those capabilities. Okay.
Thank you.
So that closes our episode for today. We're at 1 o'clock and in the East Coast anyway, so depending on where you are. And I want to again thank all our presenters, Kyle, Brian, Jeff, and David, for their excellent presentations today. And again, look for for this episode to be up on our website in the next few days, and to see you again next month. Kim, I believe it is the 25th or 26th of March.
It's 25th of March.
25th of March, that Monday. Yes. Okay. All right. Thanks, everyone.
Thank
Take care.
you. Take care.